Recording in progress.
Recording. We are. All right, so we are in this course, Foundations. Go to the very bottom. You can see today is April 18th. So last lecture on Wednesday, you guys will we'll go over the project, kind of an open lab to see if you have any issues. Yeah, and that's kind of the plan. And then the presentations will be on the 25th. So everyone should plan on attending class, right? And then you'll come up here and do your presentation, 15 to 20 minutes each person, and just kind of demo. So that's kind of the idea. Are there any questions about that? I guess, yeah. That's, you can always, I guess I was thinking out myself, if you connect, like I know you connect to Zoom, so I guess you could do it on Zoom, but sitting there, and that's a possibility too. Just be here so we can take a look at it. Yeah, so that's kind of the plan for this week. And then there's the clustering topic. So I'll probably save that for the 27th. If everyone has pretty much presented by then, there's nothing else, we'll just meet for that last day. I'll go over clustering. I guess even on this Wednesday, if we're done quickly with the projects, I do want to give you that kind of to help out just in case there's any major problems. But if everything is smooth for the presentations the following Monday, then we may just go over clustering on that. All right, so that's one last topic, but I want to wrap up today the multi-layer perceptron code that we started on Wednesday. Are there any questions? I graded your exams also, so everything, all your grades should be in, right? So you can check if you have any questions. All we have left at this point, there's no homework assignments, correct? Left? Oh, yeah, so there's no homework assignments. So really all you have left is your term project and you have your final exam, okay? Final exam will be on Monday the 2nd. So we'll do the same format that we did before, just, Zoom, right? Kind of a take home kind of an exam. Yeah, so that will be the idea. So I'll give you a few problems and then you need to. And we went over all the details of the exam as well. So that has all already been taken care of. All right, and then there's some people on here. All right, so I guess before I begin with the class today, are there any questions? No questions? Okay. All right. And then I'll learn about your projects on Wednesday. All right, so let's go ahead. I'm going to start up the Jupyter Notebook. All right, and I'm going to share the screen here. Okay, so let's go to the desktop. And then, yeah, 2022, I think. So I think we were, yeah, MLP from scratch. So this is the one that we were looking at, okay? So I'll just kind of do a review today of where we left off, and then we'll complete it. Remember, as I said, I've already given you TensorFlow and Keras. As you saw in those examples, we implemented logistic regression, a multi-layer perceptron, and deep learning in TensorFlow. And that's the pipeline that you should always follow, right? So you learn TensorFlow, The other powerhouse is PyTorch. That's more of the Facebook Meta, whatever it is now, library. So those are the two powerful ones. There's in the landscape, there's a NumPy one called JAX, I think. So it's still unfolding, so we don't know yet. So I haven't committed any resources as I have gotten burned before with these things. So, but TensorFlow certainly, and Keras in particular, seems to be a good one for you to learn really well. And also PyTorch would be a recommended one. You know, as you guys become seniors, we do teach 2 grad level courses here. One is applied machine learning, which is PyTorch. And that just goes into no more, you know, like foundations, obviously, that's more like applied. And then there's the deep learning, applied deep learning, which is transfer learning. So that's definitely like state of the art. So yeah, but those are grad level courses. So anyway, so hopefully just to kind of complete here, the theory, right? We're going to complete the theory of the multi-layer perceptron, you know, and just kind of get a feel for it. So the code should work at the end, but really the goal for us is to kind of understand, you know, this is an MLP. So obviously this is has one hidden layer. There's one input, there's one input layer, one hidden layer, one output layer. And in particular, what's important is that, you know, that you see that we are literally building everything from scratch. So even the weights and the biases, right? We've created, you know, individual ones for this and individual ones for that. So now the code is in NumPy. So in theory, I mean, it should run somewhat efficiently. I've never benchmarked it against like Weka. That's something that if you have an interest in, you should do. My expectation would be that because it's NumPy, it should be pretty efficient, at least in comparison to Weka. I would estimate Weka is the slowest. This code, pure NumPy from scratch, is faster, but it could be prone to like errors, like not a number, et cetera, because if the weights get too small, right? We saw that, right, in one of the examples, actually, when the weights got really small. And so that can be definitely an issue. This code is, by the way, on the GitHub, so you can just copy it from there. I'm literally reading it from the GitHub. And so that's really, you know, that's an important point. And then TensorFlow for sure, PyTorch, you know, those should be really, obviously that's Google, so they, you know, they do lots of things. But yeah, for the project, that's something you can try, although that's not a requirement, you know, just for fun for yourself. My expectation, as I said, is this should be a little bit faster than what. All right, anyway, so let's go through the code. So we had our libraries, and then we define all the functions that we were going to need. We also did this in an object-oriented programming fashion. So we have, you know, the function normalize, which is, you know, I've always said you should always in machine learning normalize your data, right? And we've talked about that extensively. This function that I called categorical, really, I should have called it to one hot, because that's really what we're doing. And we've talked about that concept. You can see it here. The accuracy score function, that's just a standard function. Cross entropy, we've talked about the theory of this, but obviously this is a little bit more, we've never implemented it. So now we're going to implement the equations. Remember, when you implement, there is, as I've said before, there's the mathematical theory, what you do by hand, right? Like literally, you use your brain and solve things by hand. Computers can't always represent all of that, right? So computers can only do approximation. So even an integral is not, let's say, the perfect infinite integral, right? Because computers are not analog machines, they're digital. And so because of that fact, we're actually just approximating things, but with very high precision. All right, so what that translates into is that the functions that we use a lot of the time are simplified versions. If you remember when we did naive Bayes, you know, I canceled all the denominators, right? Because we were really comparing 3 things. They all had the same denominator, which was really a constant, so we could cancel it out. So this takes some of those assumptions as well. So the equations that we use are always like the equations that have been found to be the more optimized to speed up things and get rid of some theoretical things that are just unnecessary. You know, like we said that. So just keep that in mind, but they will look similar. However, also it is not actually recommended when you write your code that you use equations straight out, and instead you should use the built-in system functions, right? So Keras will have a function just called cross entropy, okay? And I think we saw that. So, and that's because the function will handle a lot of things like not a numbers, et cetera. It'll have a lot of logic to deal with those things. Okay, so, but here, just to kind of to tie this back well to the discussion and the lecture, you know, we'll do that. Okay, so that's really an important thing. We are taking an object-oriented approach, so that kind of just makes it nice, you know, to also get that feel for the object-orientedness of it. So we've got cross entropy, right? So we'll talk, you know, as you can see, this is where a lot of the stuff is happening, like the loss function, the gradient, which is the derivative of the original function, etc. Okay, and then we've got our activation functions like sigmoid, relu, softmax, etc. And then here, this was basically the main class that we looked at. I don't remember if we actually finished this one. We might. It looks like we did. Oh no, we haven't. We haven't finished the fit function. So in the multi-layer perceptron object, we had an init function to initialize the variables. We had one to initialize the weights, and that just means that we don't initialize the weights to just zeros, right? So we initialize them to some values kind of more randomly or with a distribution, with the assumption of a distribution. And then within that same class, we have a fit function, and the fit function basically is the function that will allow us to do the forward pass, the backward pass, and the update of the parameters. And that requires that we interact with the cross entropy. So that's why I was finishing up the cross entropy, and then we're gonna work our way back into the fit function. And then the predict function is usually just a fit function, right? But this time the weights are assumed. We're not training the weights. So we're just actually going to predict values, right, with it. And over time, as we do the training, it should get better. And then everything else down here is just, you know, the very usual things we do, like loading the data set, normalizing the data set, converting the Y's to one-hot encoding, doing the train test split with sklearn. Then we create the object multi-layer perceptron with the number of hidden layers, iterations, and the learning rate. And then here's the fit, and then we do the predict. Notice now we're not passing the weights and the biases because they're already in there in the object, right? And this is very much how TensorFlow would work. You know, it's an object-oriented representation as well. And then here we just do the argmax of the predicted vector versus the Y test one-hot encoded, so that we can actually compare the values and do the accuracy. All right, so that's basically the idea. So now, hopefully we're all caught up and we can go ahead and, we can go ahead and just complete the code and then run it. And that's really the plan for today. So we should be able to finish this today, I would think. And that, as I said, is just, that would definitely complete the theoretical discussion of neural nets, right? So our journey from the perceptron to linear regression, to logistic regression, to the multi-layer perceptron. And then from here, you can see the intuition. If you're bored during the summer, try to make this into a deep network, right? You could, right? In theory, you could probably make your own from scratch deep neural net. But as I said, at that point, it just doesn't become practical anymore. All right, anyway, so we've looked at the accuracy there, accuracy score, it compares the values. I'm kind of going backwards. We have the argmax, we predict our values, so that's also done. We have the fit, we have the multi-layer perceptron there, the learning rate. Okay, we have the train test split. We have two categorical. Okay, and then we have our data set. So then we have the predict function. So that's already done. We do a dot product there between the X's and the Y's plus the biases. That gives us hidden input. Then hidden input goes into the hidden activation. That gives us hidden out. That's the first layer, hidden layer. Then that layer gets multiplied by the other set of weights, self V. Here, you can see that there. Oops, sorry, down here. And we add the bias to it, and that gives us output layer input. Output layer input then goes into the output activation, and that gives us Y pred, right? And so that function should be done. And then we are kind of here, but to complete this code, we need to make a little bit more sense out of the cross entropy function. So let's go back to that one. The cross entropy class, actually, I should say. So this is where we were, right? So we're defining these. So we have cross entropy. We do the init. All right. Then we have the loss function. So this loss function takes Y and P, which are the two things that we are going to compare, right? So we've got, if we look, loss YP should be calculate loss. Yeah, so Y and P in the loss gradient should be the Y real and the Y predicted, okay? All right, so we're just gonna say here in the code, Y is real. Oops, let's add a comment here. So Y is real. And P is equal to predicted. Okay, so predicted. So this function, then the loss function takes, you know, Y and P, and then basically we're just going to plug them in the equation. All right, so this is the equation that we saw before for cross entropy, right? Do you guys remember that function? What did it look like? What was the value in that? It had to do with logs. Do you guys remember that? Log values. So here we can do, for instance, minus Y, okay, times np.log, np.log of P, okay, minus 1 minus Y times np.log of 1 minus P. Right, so you can see the Y is here, the P is here, right? So this is the real, this is the predicted. Do you guys remember the logic? So if Y is real, if Y is real and if Y is 0, right, then this whole term cancels out. Do you guys remember that? And then all we have left is this other term over here. If Y is 1, what happens to this term? If Y is 1. Can you guys, it cancels to 0, right? Because if Y is 1 minus 1 is 0, the whole term becomes 0, and only this one becomes active. Do you guys see that? So that's that whole thing with the graphs going up and down that we did in a previous cross entropy. Is that clear? Yeah. Noah? All right, good. So it's a nice trick, right? It's a nice trick that we can just use one function or the other function, and then we can just optimize for it to minimize the value there. All right, and so we just throw that in there. So that's literally the equation. However, what's going to happen is we're going to have some 0 divisions because the values can get pretty small. So This is very common when you use equations. You have to use clipping. It's a common error. So that's why I always, although we'll go over it in the lecture here, I don't recommend writing these out. The only reason that you should write these out is like if you have a loss function and it's not this one. You know what I mean? Like if you guys, let's say that you said, oh yeah, and by the way, my loss function is this plus a regularization parameter because, whatever. You see that? You're adding things to it. This is still a linear function, and you can add as many parameters as you want, and it's going to change the optimization of it. You see that? Like if you wanted to say here, oh, plus, I'm going to look at some distance function between these two values, and I want to minimize that as well. You see, so you can add terms. So in that case, you may need to write out the equation. But that that's going to be after like a year of research, right? That you arrive at this like insight where you're going to add something like that. But for the most part, most of our models nowadays, we use the built-in functions like cross entropy, whether it's binary or multi-class. This should be binary, I think. So that's kind of what, yeah, it is binary. So that's kind of what we're doing. The multi-class function is a little bit different, and you would have to code for that one. All right. So anyway, to avoid the division by 0, then we're just going to do we're going to do clipping of the p-value. P is the predicted value, so the y's are 0s or 1s, so they don't, they're not going to change, but the predicted values will. And so what you do is you use numpy.clip, and it's going to just clip within a range, the values, so they don't go beyond or above certain things. So here I'm going to say for P that the clipping should be within 1e minus 15 to 1 minus e minus 50. Remember, this is just exponential notation. Okay, so add zeros in front. So that's 15 zeros, right? In front of the values. 0.00, 15 of those, and then the number. So that's what we're doing here. As I said, if you use built-in functions, you don't have to worry about things like this. But this yeah, go ahead, Noah. Yeah, but I think it has to do with the number of zeros that are allowed. It's not so much that it is 0 and 1, because we are learning things to be like a probability. It's about the fact that, remember, I'm going to predict, and it's my precision is 0.00000 versus 0.00000. What if it's, remember when we had that problem, how many zeros were we getting? 500 or something, right? That thing will not work. So that's what this is doing. Does that make sense? All right, yeah. So it's only about like the floating point limits, right? The limits of floating point itself, but the values are still within 0 and 1 because we are still predicting probabilities. All right, so I had to do this, and it's only because of that. But that's the equation, right? And then after that, and I believe it's right. So unless I have a typo in here. Okay. Yeah. And then we did the accuracy function. So that's self YP accuracy score, argmax. So we had done that one. And then that just leaves the gradient. And the gradient is really the derivative. All right. So in this case, what that means is whereas the loss is the same as the original function, right? The gradient just means the derivative of it. Okay. So in this case, it's so why the derivative? Do you guys remember that piece of detail? Why do we need the derivatives of functions? Anybody remember? Forgot to set up my time. All right, so Why do we need derivatives of functions? You don't remember? You've never taken calculus. Well, now there's a reason why you should. No, actually, you don't need that much calculus. And what you need for deep learning, you don't need it. First of all, you don't need it. But if you're just curious, right? The only two math courses that you need are probably three. You need linear algebra. I would strongly recommend that. You need differential calculus, which is differentiation, and then integrals, right? So derivatives are differential. And basically the idea is you explore a certain set of techniques, but here there's a usefulness of one of those. And we're not even using all of it, right? And so for instance, remember that we've said that whenever we represent the function, so y minus y hat squared, right? This function here, what's important about it is the squared. When you have a value that is squared, it has this shape. It's a quadratic shape. Do you see that? Polynomials are functions that look kind of like that. Kind of crazy. And then neural nets are even stranger, right? We don't even know what they are. Like literally, they're very complex. So remember the idea that we have a giant, right? We have a giant that's walking on these mountains. Believe it or not, at every point in this function, at every single point, imagine that's a large amount, given the learning rate, we're going to estimate at that point the derivative of that function. And that's just a technique that tells us something about this function. It tells us that what is called the derivative, which is called that gradient, it'll tell us that there's a tangent that touches this line. Basically, that's what it means. And so what's important about it from the deep learning point of view is that the shape of that tangent tells you the shape of the curve. Do you see that? So remember, you don't magically know if you should go in that direction or that direction with the weight. Remember that this is the weight. You see? So the question is, do we add a delta, whatever, delta something to the weight, or do we subtract a delta to the weight? Do you guys see that? A little piece. Well, if we add, that means we go in this direction, right? So it means we end up at that point. Would you agree? Yeah. So, we added a little bit, boom, 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 we're there now. What if you decide to subtract a little piece to that weight? Well, in terms of the function, we end up here. Do you see that? Which one of those two is best? Subtracting, right? Because your goal is the function is a function that on this axis is cost, and you're trying to minimize that. So you're actually always trying to find the bottom one. Now, the bottom of this is actually this one. But in deep learning and neural nets, you're not guaranteed to find the optimal. You're just not. That's why you always do this multiple times, and it's almost like, imagine you're dropping like a whole bunch of soldiers, right? Paratroopers, and they're landing in different areas of this valley. Hopefully one of those will get to a minimum that's the best. And you go with that one. That minimizes the set of weights, that minimizes the error. Remember that at the end of the day, that's the error, right? In the cross entropy, we're also looking at the error. Remember, we plugged in y and p, the real and the predicted. Same story, different looking function, right? Different looking function. Remember that cross entropy just looks like this, but you can intuitively think of it as deep neural nets. The deeper they are, they're a combination of many of these, right? And so they start looking like this. And so what happens, how do you know to add or subtract? Well, obviously you could do it randomly, but that's going to take forever, right? And it's highly inefficient. So basically what happens is if you instead take the derivative, and the derivative is just like if I do this, right? I have that number, right? That's the original function. If I take the derivative of that, that's going to give me that. It's like a whole bunch of rules in math that work that way. But based on this is equivalent intuitively to saying, what is the tangent of this function? So if I am here, and that's the W, the tangent will look like that. So it should be touching, right? So it's touching the point. What does that tell me? It tells me the slope of the function. So this, by looking at it, it kind of looks like that, right? So it tells me that I should go down. You see that we use that as intuition to understand how, by the symbol that it gives more than anything else. Does this make sense, guys? Yeah. So that's why we do that, okay? And so that's the idea. So if we go back to the code, you'll see that that's the thing that we're comparing here. We have, the y and the p, the two values in those functions. And now here in the gradient, we're just going to use the derivative. So a lot of TensorFlow's background and a lot of PyTorch's background is that, implementing that was really critical so that we don't have to do it. It's just because and implementing it massively, right? Implementing it efficiently. And so that's what they do. So usually when you look at PyTorch or something, you'll give it the function and then there's an equivalent function dot gradient and it just calculates the derivative for you. And then those values are very important as you start to do the optimization. So here I'm going to have kind of the same thing, but instead of the original function, it'll be the derivative of it, if that makes sense. So in this case, I'm just going to say avoid division by 0. Right? And then here we're going to, the same thing, P equals numpy dot clip and then P and then 1e minus 15 and then 1 minus e negative 15. All right, so that's the clipping. And then I'm going to do a return. And now this should just be the equivalent. So I'm going to do YP plus 1 minus Y divided by 1 minus P. All right. So I have my functions there. Okay, 3 functions. So cross entropy should be done. So now we can go back to the, I'm going to save this. We can go back to the multi-layer perceptron to the fit function and try to finish it up. So we had on here in the fit function, we had built already the initialized weights, right? So that was complete. And now we can go into the fit function. We do the forward pass. So that's just exactly like the predicted, right? That gives us Y pred. Now we can go into the backward pass and we can calculate basically the values that we're going to be using. So we're going to say, let's actually, before we do that, let's go to the updates. So here we're going to update because this will motivate. So update the parameters. based on gradients, right? So we're going to minimize the loss. So we're going to update the V values, V. We're going to update the biases for V. That's from input to hidden layer. So that's going to be self.V0. And we're going to update the weights from the hidden layer to the output layer. So that's going to be self.W. Self.W and self.W0. Okay, so we have our values here. We're gonna subtract, and instead of adding, doesn't matter. And then now we're gonna take the learning rate. So that's self.learning rate value. Learning rate times, and now come in the gradient values, right? So we're gonna just copy this one. Okay, so we've got, these, and now we're going to multiply them times the gradients that we need to calculate for from the backward pass using cross entropy. Okay, so these parameters are the ones that determine if we go up or down, that tangent that we were talking about. So we're going to say grad V, grad V0, that's the bias. Grad W and grad W0. Okay, so we've got our parameters there. Okay, and now we can go ahead here and we need to compute those in the backward pass. Okay, so we're going to have to compute grad V. We're going to have to compute grad V0. And we also need to compute grad W. And we need to compute grad W0. Okay, so these are the parameters. And so here we can just plug in basically what we need. So we're going to use let's see, this is going to be so we're going to calculate a parameter first. We'll call it grad WRT out 1 input, right? So this is the value from input to the hidden layer. We call self dot loss, loss, where loss is cross entropy. Yeah. We call that self.loss. And then that we'll call the gradient function that we defined in cross entropy. So it calls this one, okay? So it calls this one. So we're going to take that value, gradient, and that takes y comma y pred, right? So it takes the real value y that we got here, and it takes this value, the y predicted value, okay? So that we make use of that. And then we're going to multiply that times output activation. It's this one. All right, so there's one more function that we need to define. So we are basically going to multiply this times self. So this would be times self dot output activation dot gradient of the output layer input, which is this one. So it's almost like ypred. We're multiplying it times ypred, but we're multiplying it times also the gradient of that. Okay, so we'll see that in a second. But if you notice, cell output activation is actually self output activation here. But notice this has a dot gradient parameter. And that's because self output activation is a softmax, and we haven't defined softmax. Softmax will have two versions, the original and like the derivative version of it. Okay, and that's just required in the process to do the calculation. So we have that there, right? And then now we're going to calculate the V. We're going to take this parameter that we just calculated here, and we're going to run this through a dot product. So we're going to multiply that terms times hidden output, which is this one here. Okay, so we're going to multiply it times hidden output. Transpose of it, and then dot product. So that's pretty much how we calculate the weights. So the weights are basically that multiplication. And that's then, to calculate the biases, we're going to take this parameter and we're going to take the sum of that. And that's going to be the bias. NP dot sum of grad output one input on axis equals 0 and keep dimensions equal true. All right, so that's the backward pass. So certainly this part is the most complex, and this is why, like in TensorFlow and PyTorch, we don't usually have to do this kind of thing, right? The next one is it's kind of repeating this process, but for the hidden layer. So this is for from input to hidden one. And this one is from hidden one to output, basically. Right, so from hidden one to output. So here we're going to calculate grad WRT hidden one input And we're going to basically try to repeat the same ideas. So now we're going to take we are going to take the V, which the V would depend on this V, right? So when we modify this one, we would modify V. So we're going to take self V dot transpose okay, and we're going to do the same. We're going to do a dot product here between the previous one, this one, okay, so that one, WRT output 1 dot product. So we multiply times this. Okay, and then we multiply that times the, this would be the hidden input, basically. Hidden input. Okay, and this runs through an activation, so self dot hidden activation dot rate. All right. And then now, one thing I want to check. Now notice that the W's are actually the parameters between input 1 and input and the hidden layer, and then the V values go from hidden to output layer. So that's kind of important. That's why this is hidden 1 and this is output layer, actually. That makes sense. So the way I have them, they're inverted. It's almost like this should be here. All right, and then now we take X dot T dot, but it makes sense, actually. Why are they inverted? Backwards, yes. That was confusing me, actually. And then I just, yeah, you caught it before me that the reason why it's like this is we're going backwards. So it makes sense. We're going from output to input. Yeah, good catch. All right, so X transpose dot, that would take this grad hidden input. All right. Right, so xt dot grad WRT hidden input. And then the last one here is going to be for W0 np dot sum. And then we just take the same value and we specify the axis equals 0, comma, keep dimensions equal true. All right. Yeah, and that should be it. So as you can see, this part is not exactly trivial. Takes takes work, but we usually don't have to do it to this level because it can be pretty tough. So this is usually what will be abstracted by something like TensorFlow. So assuming all of that is correct, we can come back and check it out. Fit should be done, and then let's just finish up the other activation functions. So we were using here several of these activation functions. So let's start with the softmax. It has two functions, the original softmax and then the gradient version of it. So I'm going to do, and softmax does not take parameters. So I'm just going to say define call self comma x colon and e underscore x, it's going to be equal to np dot exponential. So this is just the equation for the softmax. So we're just going to take it as is. But remember, the whole point is it takes values and it does what? It changes them so they add up to 1. Okay? So you can play with this function, but that's what it does. So this will take x minus np dot max of x, and then we're just going to say over the last axis. When you see a -1, it just means the last axis. Keep dimensions equal true. All right, so that's NP. I think I have, yeah, no, I have the correct number. All right. And then return E underscore X NP dot sum E underscore X comma access equal -1 dims equal true. True. And then the gradient is going to be something equivalent. Define gradient self comma x p equal self dot call. So it's calling this one, right? And then it's just going to modify. Call 2 underscores with an X in it. And then now we're going to modify it by saying return P times 1 minus P. So as you can see, that's the gradient of it. So think of it as the original function and the derivative of it, right? So both, and we use softmax in the prediction. As is, we use this one, but in the gradient calculation, we have to do this because we want the derivatives everywhere. Does that make sense? So that's basically the idea. Sigmoid will also have ReLU, I think we don't use. So I'm just going to leave that one out. But Sigmoid will need its own pair of functions. So first, Sigmoid call self comma x colon return 1 divided by 1 plus np dot exponential dash x. Okay. And then here define the gradient version self comma x colon, and then we, it calls the function again. It calls its previous one, return self dot call of x, but it's going to multiply it times 1 minus self dot call of x. All right. So that's basically the idea. That's your, I think this is all the code. And then we'll kind of summarize it towards the end, but let's take a look. Oh yeah, there's still a few more. I'm just going to copy the normalize from the website. Copy the normalize function. think these two. Just copy them here. All right, so they should be there. So if I have my libraries, I have the normalized function, I have the categorical function, the accuracy score, the loss functions, sigmoid, softmax, multi-layer perceptron, fit function. Yeah, so this should work. Right, cross your fingers. All right, so all right. Okay. Multi-layer perceptron takes more. Huh? Oh, did I? Okay, that's a good catch. Thank you. Because I was really not sure what that would be. Okay. Now it says N hidden and it's not defined. It's probably another typo. This is N hidden here. N hidden. N hidden. N hidden. So there's an N hidden here, I think. Oh, okay. Yeah, I know what this is. That should be self. And dot N here. You see that? So just a reference to it. Okay, try it and output is not defined. So it's probably something similar. Yeah, they see here, that makes sense. This is happening in there. It's happening here, this N output. And hidden and iterations, learning rate. N outputs is this one. Oh, it's probably N outputs. All right, save it. Another one. E is not defined. So it's not like this. So it's this one here. Yeah, it should be one. Okay. All right. Try again. Zero accuracy. Okay. Didn't work. Let's print y pred and y test. Okay. X test. We did the fit. X test. Comma. Access equal 1. All right, there we go. All right, so as you can see the values, the accuracy is what? 96%. And if you look the values, the first 5 are 33441, 33441. So you can see it's predicting really well. So this is a complete multi-layer perceptron. As I said, it's it's pretty much as you can see it's kind of from scratch if you want to build it here. In summary, we have the pieces of it, right? The libraries. We have a normalized function, right, which will normalize the values. We can just use built-in functions for this. This one will just convert the labels from 1, 2, 3 to one-hot encoding. We have the accuracy metric that we use. We have the loss function, which in this case is cross entropy. We have the activation function that we're using in this case, which is sigmoid. We have the activation function for the output layer, which in this case is softmax. we have the heart of this, which is the class for the multi-layer perceptron. This has an init function. It has an initialize weights function, and it has a fit function. And then after that, we have a predict function over here. And this is, just for, the inference function, basically. And so the predict function is pretty straightforward. These are just initializing variables. The challenging part is the fit function, where we do the forward pass, which is basically taking our inputs X, multiplying it times the weights plus the bias. That gives us hidden. We run that through the activation function, which in this case would be Sigmoid. That gives us hidden out. Hidden out is then multiplied times the weights V for the next, the weights between the hidden layer and the output layer. You add to it the bias, that gives you output layer, and then this runs through the output activation, which is the softmax. And that gives you Y pred. Then now you're kind of at the end, right? So you've gone from inputs to outputs, you're at Y pred, you have Y pred and Y real. Now you need to do the backward pass. So we kind of do this in reverse, right? So we start actually from here, the loss of the gradient of Y and Y pred, right? And we calculate, we take that loss, whatever that value is, and multiply it times the values in the output layer, all right? So this is the output layer, all right? Output layer input, which is this one, right? And then to it, we also calculate those values in terms of the gradient, right? And that gives us this parameter that we're going to use to change V and V0. So you can see that for calculating the weights, we basically multiply all of them. So we'll take this value times the hidden output, okay, which is this one, right? So we multiply basically that vector of values, right? And that gives us the calculation of the weights, V. So it's basically, we're looking at hidden output. And then this one is in terms of output layer. Yeah, so the way to think about that one. That makes sense, actually. So this is our network, right? Would you guys agree? Input, output, hidden one, right? So if you think about it, what's happening here is hidden one times V gives us output. Would you agree? That's basically what happens there. That's it. That equation is actually almost V times output times hidden, and to get the V values. You see that that's actually what seems to be happening there, because if you look at the code, in the code we have, this is just estimating the difference, but then here output activation of output layer. So output layer input is that last layer before the activation, right? And so we get that parameter, we modify it times the loss between these two, and then that value is grad out, and then that is a dot product with hidden output. And hidden output is this one here. See that one there? Which is from input to hidden. So it's, oops, what is this? So it's almost like the parameters in question are this one and this one, and they're being multiplied to get the V. You see that? And now here in the code, and then the other part is the taking that same value and just summing it. You sum all of it, and that's your bias. If we look at this next parameter, now we're going, we've done calculated V, and now we're headed in that direction, and we need to calculate the W's, right? So it makes sense that the W should be in terms of this one and this one, but also considering this one, right? So we're considering this one, this one, this one to calculate that one, to update basically those W's. So that should involve input, hidden, and V. And if we look over here in the code, this second part over here of the backward pass, you're going to have here grad WR output 1 input, which is this value here, right? Which this value here is just the output, basically, and then modified, right? And then this is hidden activation. So that's that middle layer. Hidden input, right? Run through the activation and the gradient. So, but it's actually hidden. This is the key. And so you're taking that and you're taking this one, which is in terms of output. And then here's the V, right? Which is the one that we calculate, you know, we calculate this V in terms of this little v. And so we multiply basically input times V times hidden. And that gives us this value. And then this value is just, if you look at it, times X. You see that? Because this is the X here, the original one. So it's basically the terms in question, as I was saying, are this one, that because this is X, right? Remember, input. This is V. This is hidden. And that gives us the W that we're looking. You guys see the relationship? So there's, you know, I'm sure there's a lot of intuitions and reason why the multiplications are the way that they are. But what's really important here is to see how, you know, how it goes. So from output, running it through the activation functions, times the loss between the real and the pred, that gives you this parameter. Then that parameter is this parameter, and it just gets a dot product with the hidden layer values, hidden output, and that gives you the V's, which, as I said, is really, you know, this part here. Okay, I'm gonna change this. Okay, now you've computed these parameters H, V, and O, and so now you look at the second part of it, and that's going to be the hidden input. That's the middle layer, because you can see that here. Yeah, hidden input. So it's this one. And then through the activation, using the previous one, that gives you this parameter times the X parameter, and then update the W's. So yeah, so that's basically the way that you, at least in this code, you calculate the V, the V0, the W, and the W0, and then we just do the standard update as we've been doing it in the past. All right, and that's pretty much the trickiest part of this, and it's the part that thankfully it's abstracted quite a bit, right? So we don't have to think in terms of the gradients at all. Now it's a thing that you can look at, but it's definitely where the complexity is of this. Now we were able to run this code, and it actually does perform really well at 96% accuracy. All right, so that's the multi-layer perceptron. That's the last of it as far as the neural networks code for the semester. The only topic that's left now is the clustering, which, as I said, I'll save that for Wednesday, right? But after we talk about your project, so we'll go over that. The clustering is way easier, and actually we'll just use sklearn. So I'm not even going to implement it from scratch necessarily. We're just going to use sklearn and get a feel for how it should work. I might actually throw in singular value decomposition again, just kind of show you another neat little trick. But we will end the semester with that one. So in summary, this semester, we basically focus more on supervised learning, I would say, than anything else, right? If you guys remember, there's supervised learning, there's like reinforcement learning, and then there's unsupervised learning. the majority of the work because is in supervised learning, because that's really where you get the majority of the like good results. Unsupervised learning is useful, but it's limited also, right, in what you can do with it. But we'll take a look at it, and I'll see if I can tie it to singular value decomposition as well. So that will be the last topic for the semester. But that's all I have for today. So I'm going to pause the recording at this time and just leave it open if you have any questions or anything that you want to know about.